You probably learned about Ohm's law in year 10 about V equals IR or I equals V over R, the relationship between the voltage across a circuit, the current flowing through it, and the resistance in the circuit. So in this particular case, we're measuring the resistance, we're calculating the resistance of a resistor using the voltage and the current. We can do that because it's an ohmic resistor. An ohmic resistor is a resistor that obeys Ohm's law, effectively. So as you increase the voltage flowing through it, the current increases in a linear way. A non-ohmic resistor doesn't work like that. A non-ohmic resistor, it might have a downward curve in the slope as you change the voltage with the current, or it might have an upward curve, or it might do something weird. So we're only required in year 11 and 12 physics to talk about ohmic resistors, or to actually calculate ohmic resistors. You can talk about non-ohmic resistors. Usually they're non-ohmic because they get heated up by the current flowing through them or change in various other ways that change the resistance. So in this case, we're going to use this guy. This is a rheostat. It's a very old school style of variable resistance. You can slide the slider along to change the number of coils of wire that you include, and therefore the length of the wire and the amount of resistance. What we're going to do is keep it constant and calculate what value we've got it set on, because it's a very good tool, but there's no calibration. I can't go, all right, I'm going to set it on 50 ohms. I can basically just say this is where I'm going to set it. So we will change the voltage using our power supply. We will read the voltage. The voltage, we've placed a voltmeter across this to know the voltage that's dropping. And because there's nothing else, everything else is wires and meters, so nothing else should be a resistance that causes voltage to drop. So the voltage we read on our voltmeter should be close to what's coming out of our power supply. So we'll change the voltage from the power supply, read it on the voltmeter, and then the current is flowing through the ammeter and around through the circuit, and we'll measure the current as it's flowing. And then if we graph those two things, we can find out the resistance of this particular resistor. So if I turn the power supply on, we've got it set to 2 volts. We did a tricky experiment beforehand to double check that our meters were not going to blow up and our power supply wasn't going to blow up with our circuit. So we made sure that it's within sensible readings. And at 2 volts, we get about 2 volts, a little bit over on our meter. Remember that this is, the power supply is 2 volts. That doesn't mean 2.00 precisely, it means 2 volts-ish. And so that's what we're measuring, a little over 2 volts on there. And our current is, the scale that we're on is the 500 milliamp scale, so it's that middle scale. It's about 150 milliamps is what we're actually measuring as a current. So at 2 volts input, that's the current that we get through this particular resistor. We can go up to 4 volts input. At 4 volts, we read, again, very slightly over 4 volts on the voltmeter. And on the ammeter, we read a little, about 250 milliamps, 260 maybe. So we can measure that precisely with the meter. And we've got our second reading. We can go to 6 volts. And for the voltage, we get around about 6 volts, a bit over again. So this is an overclocked power supply. It's giving us a little bit more than it says on the label. And we've got a little bit over 430 milliamps at that. So we won't go higher. We could go to 8, 10, and 12 volts on our power supply, but that would do bad things to our meter, and we don't want to do that. So we've got to the end of our scale. We could also move to a higher scale and do some more measurements, but those 3 will be enough because we kind of are already assuming that it's a linear graph and 3 points is enough to establish a straight line. So that will give us a sense. We could, if we wanted to, do that for multiple values of the resistance as well and measure them. But for the purposes of this, we will get multiple data points for each of the 2, 4, and 6 volts, and then calculate and average those and graph V versus I to find the value of R for this resistor. For the ohmic resistance one, it's a nice experiment because this is very sort of commonplace to you. You know well, I imagine, the good old Ohm's law, V equals IR, we're very, very comfortable with that from earlier in our secondary schooling. So the physics isn't hard. What you're doing in this particular prac and what you're doing with your students is thinking about what are the uncertainties and propagating those, and how do we calculate our data best. So in this case, we've got three significant figures here, or 2 decimal places, 4 significant figures here. We could actually round those, and technically we probably should really have those as 10.2 and 11.9 to be consistent with our precision from our measurements. But this is what our actual voltmeter gave us in the experiment. And we've got essentially 3 significant figures here, which also happens to be 3 decimal places because of where we are in terms of scale. Now, usually our least scale deflection times a half is our uncertainty if we don't have another method of establishing uncertainty. So our least scale deflection is 1/100th here. So each of these voltages then is going to be plus or minus 5/1000ths, 0.005, because that is half of this last unit, 1/100th. So that's our precision in those. These are to tenths, hundredths, thousandths, 10,000ths. So it's one more degree of precision, I guess you could say. Although, again, if we multiplied them by 10, it would be effectively the same. So these are plus or minus 0.0005. And they're amperes in both cases. So I is the current measured in amperes. I put the units in. V is the voltage, the potential difference measured in volts. So we've got both of those. And what we're going to be looking for is R, the amount of resistance of this particular circuit in ohms. Greek letter capital omega is our symbol for ohms. So what we could do, one way we could do this is just calculate V equals IR, or in this case, if we rearrange to make R the subject, R equals V over I, not the other way around, and create an extra column, which was our R column. That's getting messy. Calculate all of our numbers, and then average our numbers. That's a method that works, but it's less accurate than the method we're going to use, which is graphing. So what we want is to be able to actually draw a graph, draw a line of best fit, because that's going to take into account better than calculating the averages, whether some points are just wildly off. A line of best fit, just working out the averages, the results and then averaging them, gives each data point equal weight. But if you do a line of best fit and it turns out that one of your data points is miles off, then you weight it less in your line of best fit. So it's a more accurate method. So in this case, we want to calculate R equals V over I. So we're going to make a graph. I'm drawing freehand here. Obviously, you will use a ruler. And given that we want to find the value of R, we're going to find the slope of this line, and we want it to be rise over run V over I. So we're going to put V in volts on the vertical axis. We're going to put I in amps on the horizontal axis. And for each of our points, so our first point, obviously you're going to, but I'm just going to very roughly do this by hand. So 2, 4, 6, 8, 10, 12. So I was a little bit off with my doing it by eye, but that's enough to give you a sense of what we're doing. And what do we get up to with the amperes? Basically, we're going to get up to somewhere around 1. So I'm going to call that 1. I'm going to call that 0.5, and then it's going to be 0.1, 0.2, 0.3, 0.4. It's pretty rough. 0.1. My graph clearly is not going to have the right kind of slope on it, but you get the idea. So if we plot our first point, it is 2.18 volts. So we're going to go, that's our 2. Our 2.18 is going to be a smidge above that. Part of the way to 4, it's going to be a point. Now you're going to have a point, but in this case, what we want you to do also is vertical error lines, or vertical uncertainties. So you know that you can do a line, and it won't be very big because 1 part in 1,000 isn't particularly big in the scale of 2 volts, but you'll have a small vertical error line on your graph. And for each of your other points, and I'm just going to very roughly kind of by eye put in something that looks feasible or plausible maybe, and each of these will have those error bars on them. And you can already see that I've kind of artificially introduced an outlier. But now we shouldn't start from here. This is not a data point. We didn't measure 0, 0. It's plausible that it would be 0 amps when there's 0 volts, but we didn't measure it, so we're not going to include it as a data point. So we're just going to draw our line of best fit. I would obviously use a ruler in the lab. That's my line of best fit going through as close as possible to as many of the lines. And you can see this guy really is kind of a weird number. Now, that's just me doing it by eye. That's not that data point. So if you get to the 8 volts or the 10 volts, whatever data point, and it's not wildly off, that's okay, because I didn't actually graph the data that's in the table. I'm just illustrating the points in the approach. The key thing really with these error bars is what you can do is calculate a maximum and minimum value of the slope. So you'll do your best possible error bar, your best possible best fit line, the most accurate you can get, and that will be the R that you actually calculate. So your R will have some value and you'll actually figure out what it is in ohms. But also, if you go through the top of the error bars at the bottom of your graph and the bottom of the error bars at the top, you can have a line with a lower slope. So that's going to be a different value of R that is slightly lower, a smaller resistance. And by the same token, if you go through the bottom of the error bars at the bottom and the top of the error bars at the top, you'll have one with a bigger slope, and that's another bound of your uncertainty. So this is a big part of what this experiment's about. It's about working with graphs to be able to quite precisely calculate the uncertainties of our results that we actually use. So if you use those uncertainty values and work through the process, I think you'll find that you're drawing your graph, draw it really big, draw it with a very fine pencil and draw it very carefully, and you should be able to actually calculate a minimum, maximum, and kind of the best fit you can see value for the value of R. And work out the precision of your experiment as well as what the resistance of this particular ohmic resistor that we were measuring is.